So we now move into a new topic which are called properties of regular languages. So we talk about what are the different closure properties of regular languages. Closure here means that if I were to take two languages that are both regular, so both L1 and L2 are regular, and I were to perform an operation OP on the languages L1 and L2, OP can be a union operation, an intersection operation. In this case, OP is a binary operator. It takes in two languages. It produces a third language, L3. Closure properties are properties that state over these operations OP that given to regular languages, the operation OP produces a third language which is also regular. So L3 is also regular. So we will look at some binary operators OP and some operators OP which are unary. That is, they operate over a single language L1 and produce a second language L2 such that L1 is regular and L2 is also regular. Alright, so let us begin. So the first operation we consider is going to be the union operator. So we first look at the closure property that states that the class of regular languages is closed under the union operation. So what does this mean? So let's take two regular languages. One is what we've already seen, the language consisting of words that start and end with an A. We call it LAA. And the class of languages that start and end with A, start with an A and end with B. So LAB. So both languages are regular. What would their union look like? Their union will be all strings that start with an A and end either with an A or a B. So I could have the string A followed by an A, the string A followed by a B, the string A followed by an A followed by an A followed by a B followed by an A followed by a B followed by a B, A followed by an A followed by a B, and so on. We can enumerate this entire language in increasing order of length of string such that each word starts with an A and ends either with an A or a B. This is what the union looks like, and our claim is that this particular language consisting of these strings is also regular. How can we prove it? So let's not go into the formal proof of the closure property, but we will look at it from a more intuitive perspective of drawing a finite automata. So let's say we had a machine, an NFA or a DFA that would accept the language LAA. So let's call it MAA. Alright, so MAA has a start state and a final state. Okay, so this is MAA. Similarly, we can have a machine MAB. By virtue of the fact that LAB is regular, we can draw a DFA for it. We can have MAB again with a start state and a final state. Now, since a word from the union will either be accepted by MAA or MAB, if we ran AA on MAA, MAA would accept it, but MAB would reject it. But one of them is accepting it. Similarly, if we ran AB, MAA would reject it, but MAB would accept it because AB belongs to the language of MAB. So if we had a mechanism to say that if either of the machines accepts a string, then it belongs to the union, and we could draw a DFA for that or an NFA, then we could say that the union is closed under is a closure operation for the set of regular languages. So how do we do that? So we introduce the new notion of an epsilon transition. Now the epsilon transition works as follows. So we start with the start state of the machine M, which is the machine for the union, that is LAB union LAA. This is the union machine, and from the start state, non-deterministically, we can go either to the start state for MAA or to the start state of MAB. Alright, so what does this mean? So for non-deterministic finite automata, we said that from a particular state, you could have more than one transition labeled with a particular symbol. Now in this case, the epsilon symbol is a special symbol. It means that I do not read anything from the input. So I can, without reading, choose to go either to the machine MAA or the machine MAB, the NFA or DFA for MAA, the NFA or DFA for MAB, non-deterministically. That means that I will perform all possible combinations of paths in MAA and MAB. Similarly, if this is the final state for MAA and a final state for MAB here, we have a final state for the overall machine, and you have a similar epsilon no read operation once the entire string is read, taking you to a final state for the overall machine. So what essentially does this mean? This means that if there is some path in the machine that on reading the string takes you from the start state through either machine MAA or machine MAB to a final state, the string will be accepted. Please understand that the string ABA will go through MAB and not reach a final state, and therefore will not be accepted. But ABA will go through the DFA for MAA, reach a final state, and take an epsilon transition without reading anything and reach the final state of the overall machine. A string like AAA, had this been an NFA, the string AAA would pass through the machine MAA. You would read the first day, the second day, and possibly reach a final state. On the third A, however, before reading the third A, if you chose to take the epsilon transition and go to the final state of the overall machine, that particular path would fail, because on this last A there is no transition out of the final state. Alright, so AAA will be completely accepted by MAA. Once the string is over, you would take the epsilon transition going to the final state of the overall machine. So we move on to the next closure operation for intersection. So the intersection operation states that the intersection of L1 with L2 produces a third language L3, which is also regular. Now to prove this, we do the following. Since L1 and L2 are both regular, we can construct NFAs for L1 and L2. Let N1 be the NFA for L1 and let N2 be the NFA for L2. N1 is therefore defined as Q1 sigma delta 1 Q01 and F1. N2 is similarly defined as Q2 sigma delta 2 Q02 and F2. The next step that we take is we take the cross product of the states Q1 and Q2. So we construct a machine, an NFA N for the intersection, and NFA N is going to be defined as Q sigma delta Q0 and F. where Q is going to be the cross product of Q1 and Q2. That is, Q is equal to Q1 cross Q2, which is the same as saying that we will be having pairs Q1 Q2 such that Q1 belongs to the set of states from N1 and Q2 belongs to the set of states from N2. This is what Q1 cross Q2 will look like. Alright, now what will be your final states? The set of final states will be the set in which you will be both in a final state in N1 and a final state in N2. So let me repeat that again. You see, the purpose of N is to accept those strings that are accepted both by N1 and N2. So if a string is accepted by N1 but not by N2, we should not accept it. Therefore, you can be in a final state in N only if the string is accepted both by N1 and N2. So F is going to be the cross between the final states F1 and F2. That is, the set of states Q1, Q2 such that Q1 belongs to F1 and Q2 belongs to F2. I could be in a state in which Q1 is a final state of F1 but Q2 is not a final state. Such states will not be in F. Your transition function will move in such a way that on a particular symbol you will be simulating both N1 and N2. So delta of the state of Q1 comma Q2 on a symbol A will be a new state, which is a pair we obtain by simulating N1 with Q1 on an A and simulating N2 with Q2 on an A. Right? Now, if N1 and N2 are in a phase, which they are in this case, this will not be a single state. It will be a set of states. So it is essentially the cross product of the set of states you get by taking delta 1 and the set of states you get by taking delta 2. So we have a cross product here. Alright. For instance, if delta 1 Q1 on an A was Q3 Q6 and delta 2 was Q4 Q8, alright, then the cross product would be the set of states Q3 Q4 Q3 Q8 Q6 Q4 and Q6 Q8. Alright, I hope this is clear to you all. Those that have difficulty with this, please go back and watch the part on cross products. Alright. The next closure property we discuss is the closure property of concatenation. So if you take any two regular languages and you concatenate words from the two languages, the first belonging to the first language, the second belonging to the second language, put them together, what you get is a new language which is also regular. So how do we prove this? So let us say that we have NFA for the first language. So we have a start state, okay, and we have some set of final states. Okay, so there is some path from the start state to the final state, and there is some path from this start state to this final state, There could be a path from one final state to a non-final state, and from this back to another final state. So there can be any kinds of paths. This is N1. So on reading the first word W1, that is part of the concatenated word, we will have gone from a start state of N1 to one of the final states or more, one or more of the final states of N1. Now, having ended in a final state of N1, we next have the string W2, which is part of the overall string. So we have to have a seamless way of moving to the NFA N2 of L2. So the NFA N2 of L2 also has a start state and possibly a set of final states, right? So from every final state of N1, we move by a single transition on an epsilon to the start state of N2. So the start state of the overall machine N will be the start state of N1. The final state of N will be the set of final states of N2. So any word which is concatenated by taking a word from L1 and taking a word from L2, such as W1, W2, will be accepted as follows. First, the word W1, W2 will be pumped through the machine N1. It will take some path to reach a final state of N1 and be accepted. We will then, at an appropriate time when it is accepted, jump from a final state of N1 to a start state of N2 and start the process of checking the second half of the word W2, second part. If W1 and W2 are a legal combination of L1 and L2, then the entire word will be accepted. This is the closure property of concatenation. The next closure operation is the clean closure operation or star operation. The star operation is a repetition operation. So if L1 is a regular language, L1 star is also regular. What does this mean? If W is a word in L1, then not only will L1 star recognize W, by recognize I mean accept, but it will also accept W concatenated with W, W concatenated with two W's, and so on. It will, in addition to accepting W, also accept the empty string epsilon, even if epsilon does not belong to L1. So even if L1 does not have an empty string in its vocabulary, then L1 star will include epsilon. Obviously, if L1 already has an epsilon, that's also fine. It will still have epsilon. So essentially, let me state this more cleanly. L1 star allows you to have either no repetition or words with repetition or the empty string in the language. So let's say we had a non-deterministic finite automaton N1 which accepted the language L1. So what will N1 look like? N1 will have a start state and a set of final states, right? And there will be some way of getting from a start state to a final state. Now what we do is to N1, so that we can recognize L1 star, we construct a Turing machine, we construct a NFA N1 star such that our start state is also a final state. This ensures that we can accept the empty string. From the start state, without reading any symbol, I can move to the start state of N1. This is the start state of N1. From the start state, N1 will accept some word by going from the start state to the final state, and we will add a single transition from every final state in N1 to the start state. The label of the transition will be epsilon. This ensures that if N1 accepts a word, we can take an epsilon and start accepting another word in N1, thereby concatenating strings from N1. So here L1 star will have W, W1, W2, where W1 need not be the same as W2, but both W1 and W2 should be in L1. W1, W2, W3 again need not be the same, but all three must be L1, must be in L1, and so on. It's also possible that W1, W2 and W3 are the same word concatenated together. This is the machine which will accept L1 star, the clean closure. Since we can construct such an NFA to accept L1 star must be regular.